All right, so in this video, we are going to take a look at one of our optimization problems where we'll be using the derivative to help us solve for the maximum or minimum. This is actually a similar problem to something we've already done in Algebra 2, but we're going to do it with calculus right now. So we have a farmer that has 2,400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He doesn't need to fence along the river, so you'll notice we have two x's and a y, which also could be labeled as width and length if you'd rather do that. But I think x and y is good, especially because we are going to be doing derivatives. What are the dimensions of the field that has the largest area? So optimization is another way to talk about like maximum or minimum. And then we need to find that area. So we're looking for dimensions and we're looking for the area. So we kind of are going to need two different equations for this, and it will end up coming out to be something that's quadratic. Not all of them will, but this is something that we did back in the quadratics unit in Algebra 2. So our first step is to identify what you are finding and write an equation for it. Optimizing, but we're looking for a max and the min, so we want to identify what we're finding the maximum minimum of and write that equation. Substitute into to help us with finding that, in this case, maximum area. So we're looking for a maximum area times y, just because we're seeing that x and y are our length and width in our equation. Step 2, we're going to write a second equation with the information that we have. 2. So sometimes we'll start off with an equation that only has two variables and we can start our third process there. So the second equation is going to be our perimeter equation. We would have that perimeter is equal to, in this case, 2x plus y, because we have that river bordering the area. And then we also have that it's 2,400 feet of fencing. So that's the perimeter that we're going to be figuring out. That's how much we have to fill in there. In fact, I'm going to keep that in red. And then we're going to pick something. We want to substitute from that into the area equation, because our focus when we are working with this is to work on the area equation. So our third step, once this stops moving on me, solve for a variable. Into that step 1 equation. And the reason we're looking at the step 1 equation is that's the one that we are trying to maximize. So it's always good to identify that one first, even though you might have more equations that we're going to be working with. So I'm actually going to take the 2,400 equals 2x plus y. We'll solve that for y. So we would get y is equal to 2,400 minus 2x. And then that we are going to substitute in for y in our other equation. So we're going to put it into this space right here. Make sure to use parentheses. I mean, that's a given now when we're substituting all that information in. That's something we've done a lot of at this point in all our different math courses leading up to this. So a is equal to x times 2,400 minus 2x. We just want to simplify that a little bit. We get area is equal to, and I'm going to put this in, I guess it doesn't really matter if we put it in descending order or not. I'm going to keep it as is. It would matter if we were using this and solving it with a quadratic, but since we're not, and we're going to be doing derivatives, you can keep it in this order. You can put it in descending. Either way, it doesn't matter. So this is the area equation now. We have two variables. We have a and we have x, so we should be able to take the derivative. Remember, taking the derivative helps us find our maximum or minimum points. In this case, we're maximizing, so it will help us with finding the maximum. Weird. So different ways you can write notation for this. You can either write a prime, or you can write dA over dx is equal to. And our derivative for this will be 2400 minus 4x. So what you'll notice, the derivatives will be some of our normal power rules. Occasionally we'll get some fractions in here, but for the most part, mainly power rule derivative. It's setting up the equation that's going to be the harder part initially. So we're setting this equal to 0, we're solving, we will get negative 4x equals negative 2400. Divide by negative 4, and we'll get x is equal to 600. And we were working with feet, so this will be 600 feet. That is our x value, one of our dimensions. This could be the width, it could be the length, whatever you decide to make it. Step 5 is to solve for the other unknowns, and you can do that how you want to. So we have a lot of equations that we can plug back into. Once you've found that derivative, usually you would plug back in that answer to figure out the maximum area. And then also make sure to answer the question. So this question is asking what are the dimensions? So we want to just recap that at the end, and then what's the maximum area. So if we take our equation of a equal, we could do a couple different things. We have y equals and we have a equals. So if I do the y equals equation from up top, which was the 2400 minus 2x, I can plug my x into there and find my other dimension. I could plug the x into my original a equation to find the max area, and then find the y value either way. So y comes out to be 1200. And then it's up to you. We have the two different dimensions, so with area, at this point, you could plug into the equation that we came up with, or you can multiply the length times width, which we just found. So I'm just going to do a little box with all the information. We have dimensions, are 600 feet by 1200 feet. I'm going to squish that in there, sorry about that. And then our max area, the optimized area, is going to be 720,000 feet squared. So back when we did this in Algebra 2, we came up with the vertex because that was the maximum point. And in fact, the vertex, which would have been negative b over 2a, is the same thing that we're getting when we're taking the derivative and setting equal to 0, just a different technique. And it flows a little bit nicer because we now know that to find those maximum points, we can use the derivative. So it's a little bit of a smoother process, a little bit quicker than what we did previously, and can be used for things other than just quadratics as well. All right, so that ends the video. The practice questions that will go along with this will be practice 1 and 2. That will be trying out very similar types of questions to these.